So what am I saying here? So I'm saying that the limit of, well, we don't know limit notation yet, do we? So basically, you put really small numbers into f of x equals 1 over x, and really huge numbers come out. So that explains why, and something got turned off. That explains why when I graph the function f of x, where f of x is equal to 1 over x, as I approach the origin here, it's like I'm putting in 1 over n for really big n, and so what does that do? The function takes 1 over n and it spits out n. So as these n's get huge, it makes this fraction move towards the origin, but it makes the value of the function explode because n is getting big, right? And the function is outputting those n's. So they're going way up here like this. Alright, so that explains that part of it, and why does it kind of slowly go down to the x-axis like this? Well, here's the equation. The equation tells us what's happening. So we can see from the picture, or from what is supposed to be the picture, that as x gets really big, the output is getting really small. So remember, the output of the function is what tells you the height of the curve, right? So I mentioned that in class, and I said everybody always forgets it. So if you put something like x into the function, the height is f of x. So what is going to happen to this as x gets big? As x goes to infinity, f of x is going to go to, what, it's like 1 over infinity or something. So I don't know what that means, but I can imagine what 1 over a really huge number would look like. What is that going to be like? So, like, what is this? I just wrote 100 million. It's kind of like infinity. It's really close to 0, right? So what does this say? This says how many times does, I'm just reminding you what the division notation means, what the fraction notation means. So how many times does 100 million go into 1? Like practically 0, right? So this is practically 0. And that explains why this curve here is going down to touch the x-axis. It's because as x goes to infinity, the output is looking like this. It's looking like 1 over a million bajillion. 1 over a million bajillion is going to get closer and closer to 0, and that's why this curve is moving closer and closer to the x-axis. Alright, so the important thing is just to remember the basic shape of the hyperbola. So there are several functions, and you just have to memorize what their shapes are. So one of them is this. So you should know that 1 over x looks like this. And in fact, there are other functions that look like this. Let me just bring up my calculator here. So let's look at 1 over x, that thing that I was just telling you about. So there's 1 over x, and let me make this line fatter. So there's 1 over x, and these plotting machines don't handle, you can see it made a blue line here, a vertical line. It's because it thinks that everything it's plotting is continuous. It's a dumb machine, right? It doesn't realize that the function is actually not defined at 0, so I'm sorry about that. But the function looks more or less like what I said, and what I was going to go towards was saying that there's a whole family of functions that look like this. So in that family, 1 over x is just the first one. And what's the next one? So the next one is 1 over x cubed. I'm going to show that 1 over x cubed looks basically the same as 1 over x. And why? Because the argument that I gave up here for why 1 over x looks the way it does, everything I said about 1 over x is also true for 1 over x cubed, right? Both those things are true. As x goes to infinity, 1 over x cubed goes to 0. And as x goes to 0, I put in these 1 over n's. And if anything, for 1 over x cubed, it's even worse. Now if I put in 1 over n to this thing, n isn't going to come out, n cubed is going to come out. So as you put in these really small fractions, 1 over x cubed explodes. And let's just show that it's true here. So what happens if I change x to x cubed? You can see it just gets steeper. And what happens if I replace it with 5? It gets steeper still. If I replace it with 7, it gets steeper. If I replace it with 9, it gets even steeper. You can see what's happening. It's the same basic shape, but it's getting steeper and steeper and steeper and steeper and steeper. Alright, and you can imagine if I were to put in like an infinite odd number or something, whatever that means, it would just look like kind of an angle there at 1. Alright, so why do I keep putting in odd things? When I went here to, when I went to the next thing in this family, I went to 3, I didn't go to 2, and that's because when the powers are even, the shape looks a little bit different. So when the powers are even, it looks like this. So this is what 1 over x squared looks like. So let's say that, I don't know, I feel kind of compelled sometimes to write that equals y, because that's the equation that really describes the curve, right? This curve, this graph, this is the set of points in the plane that make this true. So any x, y here on the curve makes that equation true, and if anything makes this equation true, it is represented by some point on this picture. So that's why I like to write the equation. Alright, and why does this one look a little bit different than it does when you put in an odd power? It's just because if you take a negative number, so here these are all negative numbers, if you take a negative number and raise it to an even power, like negative 5 squared, it's positive 25, right? So that's also true for any even power, because if you multiply something negative times itself an even number of times, then we can match up the negative signs, right? The negative signs get matched up into pairs. And so that makes any number to an even power is going to be positive. So for these functions where the power, here the power is 2, which is an even number, so when the power is 2, or any even number, this lobe over here, this part, is above the x-axis, and it's just negative over here when the power is odd. If you try to make this argument about matching up the negative signs, if you raise negative 5 to an odd power like 3, or any negative to an odd power, it's odd, so you're going to have an uncancelled negative. So these two negative signs pair up and they annihilate each other, but then there's this crazy one left over, and so this is going to be negative 125. Okay, so for any odd power, this negative lobe goes down. For any even power, it goes up. And we can see that if we look at the calculator, which has disappeared. So now instead of 15, let me change this to 2, and it's just like we were saying. So now I'll change it to 4. Now I'll change it to 6. Now I'll change it to 8. Now I'll change it to 10, and so it just works the same way. It's just that the negative part goes above the x-axis now.